my colleagues at Southern Plains Transportation Center and Oklahoma DOT, I would like to welcome you all, to this seminar. This is a set of seminar that is offered by SPTC. So before, I just wanted to let you know that we'll be using your login information for PDH. So please make sure that you're logged in, and we're going to get a list, from our IT at the University of Oklahoma that will show your login time. So PDH is going to be given based on, and keep yourself muted so that we do not have any feedback from anyone. We appreciate that very much. So before I actually ask Dr. Molina to introduce our speaker, I would like to also announce our next seminar. So I think Dr. Nasim Uddin, you probably are sharing your screen. So if you stop sharing your screen, then I can share mine to announce the seminar, and then we'll go into your screen. Thank you. So let me see if I can share. How do I share my screen? So our next seminar is going to be in a week. That would be September 30th. It will be given by someone that most of you know, Danny Gerhardt. The topic is going to be thin lift asphalt overlays, project selection, design, and construction. And it will be from 2 to 3:30. And you are also going to get one PDH, 1 hour of professional development hour. And these seminars are free, and I'm a professional engineer myself, so I look for free PDH. And of course, there are other reasons for attending these workshops or the seminars as well. So again, we want to thank you all for taking your time out of your busy schedule to attend these seminars. This is an exciting topic, and the seminar is today's seminar is co-hosted by SPTC, Oklahoma DOT, and ABC UTC, Accelerated Bridge Construction University Transportation Center at Florida International University. So with that, I'm going to stop sharing my screen, and then Dr. Michael Molina, who is the librarian of Oklahoma Transportation Library, located at OU, to introduce our speaker and also share a few logistics with you before we formally start. Thank you.
Thank you, Dr. Zaman. Yeah, as Dr. Zaman mentioned, I'm Michael Molina with the Oklahoma Transportation Library. And before we get started, I wanted to let everyone know that we will be recording this presentation and posting it on the SPTC website. Now, if anyone has any issues being recorded or anything like that, let us know and we can make arrangements for that if you're uncomfortable being recorded. Also, after the presentation, we're going to post all the slides on the SPTC website as well, so you can access that. And we'd like to ask everyone to make sure you're muted during the presentation, just so we don't get any feedback or anything like that, and to make it run as smoothly as possible for Dr. Uddin. And we will have a question and answer session after the presentation, so please save your questions until the end. And at that point, you'll be able to unmute yourself and ask a question, or if you'd prefer to type it in the chat box, you can do it that way as well. Okay, so as for introductions, Dr. Nasim Uddin is a professor and the graduate program director in the Department of Civil Construction and Environmental Engineering at the University of Alabama at Birmingham. His research program focuses on flyby sensing and monitoring of built infrastructures using UAVs and robotics, natural hazard analyses, and disaster risk management. His current NSF projects include Mobile Automated Rovers Flyby for Bridge Network Resiliency, and he serves as the editor-in-chief of the ASCE Natural Hazards Review Journal. So with that, I'll go ahead and turn it over to Dr. Uddin. And it looks like you're still muted, Dr. Uddin. There we go.
Right. So you can see the screen. Okay.
Yes.
So good afternoon, everyone. So this is it's my pleasure to be able to give you a brief overview in a high level of a couple of my NSF projects that we worked on. And thanks, Professor Jaman, to giving me the opportunity. And again, I have a large team that contributed, including many of my PhD and postdoc students, including Dr. Yahya Al-Hattab, Shengjun, and many of my colleagues. And I listed many of them, and I could note some of them. So we embarked on solving a very interesting problem that we're all aware of, and that is the bridge inspection and monitoring. And I don't need to spend any time justifying the importance of the problem. But the way we do inspection and monitoring of the bridge nowadays is using the visual inspections, which has a number of limitations. Not only that, the inspector have a challenge to access to many critical locations. Also, you have to put the lane closure in place, and then there are many challenges that including the subjectivity of the inspections and many others. So the time has come to really get up to the speed on number of high-level technology. Structural health monitoring technology came a long way, but it has its own baggage. Number one, it creates a large volume of data because it collects the data 24 hours, 7 days, and many duty actually doesn't have the manpower to analyze all those data. And if something goes wrong, it becomes a legal liability. And another problem with the health monitoring system that we have today is that you need a continuous power supply on every bridge. And that's almost impossible for many bridges. Another problem that we have, the current health monitoring system, is it only tells you half the story. Like it gives you the problem or information about the health of the bridge, but it doesn't give you the other part of the equation, that is the load itself. And another issue that once you have the health monitoring system in place, not only is cost expensive, it takes time, is you cannot easily remove it and to take it to another site. So in order to overcome all those challenges, especially the bottleneck of requirement of power supply, the large volume of data being generated, and lack of establishing relationship between the load and the health, we designed a cyber physical system. This is how the system works, that you have this sensor in place. And what we did, we set up some landing pad where a drone can fly and sit on it, and it charge all the sensors on the bridge site. And then it also download the data. So it solved these two major problems. One is the power problem, because now you don't need any source of power because drone comes every now and then and it charges the battery of the sensor, wake it up, and then the sensor continue collecting the data. It also solved the data problem because you're not collecting the data all the time. You only collect the data as you need, and drone comes and collect the data and goes back. So this really very interesting and problem, and we had to solve this landing pad problem, which is able to not only charge the sensors, but also allow the drone to collect the data. And this is the device that we designed. This is how the landing pad look like, and it has this sensory readout circuit. It has a data recovery circuit, And this is the PCB layout of the oscillators. This is the design and also the prototype board that we manufactured. And this is a receiver unit. We proof tested in the lab, and we could successfully demonstrate that this system works. But as we solve this large volume data problem, moving into as need basis data collection, it creates another set of problems. And the problem is now we have very limited number of short sensor channels, and the data length is shorter than the conventional health monitoring data. As you know, in order to detect the damage in a breeze, you need to establish a very accurate mode shape, and you need many sensors and a robust post-processing. So to overcome these challenges, we move on to a next level of research. It's like the damage detection algorithm using the short data burst, meaning a signal that has a duration less than 5 seconds. And the way we handle that, so this is like a very short data, short 6-second duration data, and then followed by pre-vibration data. So we had to now compensate the shorter duration so that we get the similar level of damage detection data that a traditional health monitoring system provides. And the way we do it, we extend this data artificially by padding. So we investigated many padding, zero padding, symmetric padding, anti-symmetry padding, periodic padding, smooth order 1, smooth order 0. And all of them work very well, except the symmetric padding and the periodic padding, as you see in these results. So this is the original signal. As you see, without padding, the error was very high. But as you do all those padding, see the error drops significantly to make it workable in a practical situation. Even when we inserted the noise into the signal in a very high level, as high as SNR equal to 5, still most of the padding technique giving you acceptable level of accuracy. So with establishing that, I think that was a major hurdle for us to overcome. We are actually focusing on some discontinuity issue between force and free vibrations. Now that we have the power supply problem resolved, data problem resolved, how we solve the relationship between the loading and structural deterioration that completely absent in today's health monitoring system. So again, we look into the same scheme we just developed, but this time we want our sensor not only give us information about the health of the structures, also give us the weight of the truck that moving through the breeze. And we call it breezeway motion. This is how it works. So this is the sensor we have below the girder. As the truck goes by, we have a wave motion algorithm that based on the strain data, it calculates the weight of the truck. And then in real time, it sends the information to a smartphone. And if it's enforceable, the police can actually give it the ticket. But our goal actually was getting the weight information about the load of the truck. So to practically possible, we had to get into some high fidelity simulation of the vehicles that include serious level detail in the tire, in the suspension, just to show you some calibration that we had to do. Like for example here, that this is the proof test of the suspension systems that was as good as experimental. So we really had to resolve those kind of detail in order to make it workable. And this is really the field test in the Georgia that we did. So as the truck goes by and our algorithm works, so we have this strain gauge, wireless strain gauge, and accelerometer that gives you in real-time data. And in the real-time algorithm, we could calculate the weight of the truck in a very reasonable accuracy, even less than 3% error, both at the gross weight level, which was very small error, even at the axle levels, we got a very good weight. But one challenge was actually, it's like when there were multiple trucks moving through the breeze. So we really, again, wirelessly collect the data in the site and then run the algorithm in real time. And we was able to get the weight of both trucks within a less than 2 to 3% accuracy. So it really works. So that was, again, a breakthrough. Now, all of a sudden, the system that we are proposing, that it's not only give you the information on the health of the girder and the breeze, it also give you the information on the weight of the load that moving through the vehicle. So now you have a complete picture of the problem. However, even though this scheme that I proposed, it solves the problem of the power, solves the problem with the data, solves the problem with the interaction between the load and the health, still the installation of this kind of system is very problematic. Not only it takes a lot of time, it has a lot of complexity to get it right, and accessing to the breeze is another challenge. Of course, cost is very prohibitive. So the challenge, next challenge we took, can we really get away with all this mess and make it simple, cost effective, and really reasonable? So the way we have to do it then, we have to somehow replace these wireless strain gauge sensors with something else. And we have to get away with all those installation time. How can you do that? Well, the drone was the solution. So imagine if we have a drone instead of a sensor that fly with an accelerometer like this small size and attached this, like what we see in the Stanford experiment, then instead of collecting the strain gauge in real time, you collect the acceleration on the real time. And does it work? So then you have to get away with installing these heavy duty sensors and all those manpower and the expensive efforts, just letting fly a drone attached to it and you're done. Is it possible? But the challenge is then, how can you replace that such kind of size of sensor with that small sensors and still giving you the good results? So again, as you see, the idea was then that we're gonna have those drone gonna fly out, attached to itself on the breeze, and as the truck goes, it will give you the weight of the truck, at the same time, the health of the informations. So the challenge is then to get a very good acceleration, because if you convert or you move from strain gauge to acceleration, then breeze vibration is very sensitive. So your vibration signal has to be very good. So if you use a silicon design, which is very expensive and takes heavy duty, it's going to give you a very good vibration signal. But if you want a drone with acceleration, like a small size sensor you have in the smartphone, then it's not going to give you as good data as this silicon design going to give you. So that is impossible to get a good data that's going to be useful to get the weight of the truck and the health of the breeze. So, like, to give an example, the kind of vibration data you're going to get from silicon design, which is very big, heavy duty accelerometer. And this is a kind of noisy signal you're going to get if you use a sensor like inside the smartphone that drone can use. So you see how noisy it is. Obviously, this signal is not going to be able to give you the weight data and the health data. So the challenge is, can I change this signal to this high level of accurate signal? So the way we do it, so we use a stochastic resonance algorithm invented by actually Benji, and he was inspired by how the cricket escaped the bird attack. And to explain to you what does mean, so his algorithm was developed based on the cricket. When he see a bird, he sends a signal to the bird, and the signal comes back. Then what the cricket does, his signal that he tried to look for is the signal from the bird. And that is very weak compared to the environmental vibration. So he artificially tune it, amplify it, and understand that bird is not flying towards it. So he got happy and he's run away, right? But if the bird is coming towards the cricket, again, it's utilized this the stochastic resonance, and it amplified that weak signal coming from the bird that is looking for. And now he can see this two pressure signal from the two wing of the bird, and he anticipate the problem and he ran away. So this intriguing theory actually understood by the Benji, and he developed this idea of tuning up the weak signal and resonance algorithm, amplify it so that you can get the good data. So that's actually involved the movement of heavily damped mass on a specific potential well. So based on that theory from Benji, we developed our algorithm, And we have now this noisy signal from the smartphone sensor. Then we are able to noise tuning this weak signal that we are looking for using the stochastic resonance, and was able to extract that weak signal in a successful way. To give you a practical example, so this is a breeze that we are investigating, and these are my students. So they are putting the smartphone not on the breeze or underneath the breeze, just on the guardrail. Even putting on the guardrail, so we got this noisy signal. But once we applied the algorithm, then we see that the breeze frequency that we observed is as good as 100% accurate that we obtained from the actual algorithm and actual breeze vibration. So 100% matched. Now that, and this is some of the comparison with the extracted signal and the first breeze frequency, and you can see the accuracy is almost 100%. Now that we could do that, now we have a system that we can have the drone with accelerometer. As you can see how small this drone is, and it has inside it this smartphone sensor, very little, and then it can fly into it. Now, by attaching itself to the girder, it can give you not only the information of the weight of the truck, it will give you the health breeze. So that kind of sealed the deal. And this is the system that we developed. It involved this drone, an accelerometer like a size of a coin, and some mini relay switch and electromagnet. And as you can see how it attached itself and then shut down the engine and then continue collecting the data. And this is some of the field experiment we performed in a breeze. And as you can see, this is the acceleration collected by the actual sensor attached to the breeze. And this is the signal collected by the drone, and is almost perfectly matched. But sometimes what happened, that is very difficult for drone to attach certain location of the breeze. So in order to solve that problem, we investigated a hovering drone. That drone is going to be hovering, without attaching it, but is still able to collect the data. So to show you this experiment, this is a cantilever beam, and it's under the load, and it has displacement. So we have a displacement sensor, and the hovering drone collecting this image data. And then if you compare, so this is the data from drone, and this is the data from the drone sensor. But once we apply our hovering drone algorithm, the data from the drone matches very close to the displacement sensor. So a hovering drone can collect the deformation data. But we are looking for acceleration, remember? So for acceleration, again, the drone is hovering here with this camera, and this is the accelerometer, and we are accelerating this cantilever beam again. But as you can see, the data from the drone camera is as good as the accelerometer attached to the breeze and the high-speed camera. So that also eliminates this other challenge of drone not being able to attach to the particular location of a breeze. Then we move on to some interesting problem, that how about instead of one drone, we can have multiple drones working together as a flock. To give an example, imagine this is a breeze here. So these three drones fly, attach itself. And then the third drone remain, and then it calculates the segment of the mode shape. Now, when you compare the original mode shape, healthy mode shape, it doesn't see any problem. So the third one remains there. The two other dance around attached to the next segment, and you get the next segment of the mode shape. And still, it doesn't see any problem compared to the original one. And it keep on moving till it find out from the global mode shape, there is no problem. However, instead, if there's a problem, so they are the first set of drone, and it compare the mode shape with the healthy one, and you anticipate a problem, then they zoom in, and they zoom in further till they find out exact damage locations. So in order to proof test this idea, we look into this breeze in the real life. And this is a railway breeze, and they have a serious damage on the bearing. So as you see, the support are damaged, and the bearing was almost gone. So they are about to replace and fix this support condition. So before they do that, we went in and we wanted to see if the mechanism that I proposed to you, can we see the difference of the mode shape from before they do the fixing the bearing and after the fixing the bearing. Because if we can, then by comparing, you could tell there's something wrong with the breeze bearing. So what we did, again, we attached these two sensors, and then we collect the signal data, then we move them one step at a time until at the end of the breeze, and we got the complete mode shape of this breeze before they did the fixing and after they did the fixing. Then we can see a clear difference of the mode shape before the rehabilitation and after the rehabilitation, meaning that if something happened to the breeze during the earthquake or flood or hurricane, and if you don't know the breeze is safe or not, then we could fly those drones and we could tell by looking at the mode shape and comparing it with the previous mode shape if something went wrong to the breeze. Then we moved on to the next level. How about instead of getting the vibration signal, can we very accurately get the image of the damage? So to do that, again, we have this drone fly around the breeze and looking for the crack. As you see, it can identify the crack and it can differentiate between the shadow and the crack. Okay, so it can do that. So that one, even it gives you the location, the crack width, and other informations. But the challenge was actually that some of the cracks are very small. So the drone has to fly very close to get them. But the challenge is to find out where exactly this crack is in the entire breeze. So to do that, we employ machine learning technology with the faster RCNN. So what we do, in this laboratory test, we look at the crack and then we look at the entire beam. And by matching the features, we could superimpose the location of the crack on the beam. To give you real life examples, how this point feature matching algorithm works. So here you have a breeze. So the drone identifies the crack, and it also identifies some strongest feature of the crack and for the breeze itself. Then by using machine learning feature comparison, it could not only give you the location and image of the crack, but also the location of the crack. Now we're also looking into some infrared thermography for that purpose. Now with that, now that we have this flyby technology work, I'm gonna move on to the drive-by technology. This is much cooler actually. How does it work? Imagine an undamaged breeze and your vehicle goes by, inspection vehicle, it tells you that this breeze is no problem. Or after an earthquake or a hurricane, you send the inspection vehicles and it says, oh, there's a problem in the breeze. Because if you could do that, then it solved the power problem, the data problem. It's like a moving sensors, it's no sensor required, it's economy, simplicity. So it can be a fantastic complement of the system that I propose as a flyby. Now, how does the drive-by works? The way it works, it can eliminate all the problems, the power supply, the data, and interaction. Why? Because if you look at interaction equation of a breeze moving through a beam example here, and you look at the response of this vehicle, this is the response of the vehicle. And right in the response, you can see hidden is the vibration property of the breeze itself. So what is cool, if we can extract this vibration property of the breeze from the signal you receive from the vehicle, that's it. That means somehow we have to identify this vibration characteristic of the breeze from the response of the vehicle. Meaning you need to extract the breeze frequency, the breeze damping, the mode shape, and all from there so that you can have discontinuity signal to give you the location of the damage and extent of the damage. Now, traditionally, the fast Fourier transform doesn't work here because it gives you very low resolutions and it's not sensitive enough to detect the frequency drop that will caused by the damages. So what we did, we investigated the pseudo frequency of the wavelet transform. And this is very cool because it's not only give you the frequency domain solution, but it also actually keep the information in the time domain. So to give you some example, so this is the simulation problem we have of a breeze, 15-meter breeze. And this is the vehicle property. These are really practical, actual data on the vehicle. And also this is some breeze property data. So once we run the simulations, we could actually calculate the frequency of the breeze exactly comparable to theory. And also we identify there's no resolution limitations. So this works quite well. Then we impose some crack into the middle of the beam, 30%, 40%, 50% crack, meaning we take the material out. And then we see, interestingly, this is the intact breeze, the level, depending on the level of the damage, 20% damage, 40% damage, 60% damage in the cross section, we could clearly see the drop of the frequency, meaning that we will be able to see if something went wrong in that breeze locations. But the challenge actually is that this calculation is a function of the velocity of the vehicle, meaning that this frequency calculations is not actually good calculations. It depends on the velocity of the vehicle. Like higher the vehicle speed, the lower the frequency. So this is one significant limitation we need to overcome. Second is, once we included the damping ratio of the breeze into the equations, we could see that the mode shapes are impacted by the damping ratio of the breeze. So by reverse algorithm now, we could calculate not only the damping ratio of the breeze, also the mode shape of the breeze from the response of the vehicle. And as you notice, however, as the speed increases of the vehicle, like 10 meters per second, the accuracy of the damping ratio drops. Similarly, the accuracy of the mode shape also drops. So we need to overcome. And finally, we know that road surface is roughness. So roughness can be very detrimental to the high mode frequency, because high mode frequency has a low amplitude that can be overwhelmed by the breeze vibration. So we improve our algorithm to correct those errors from the roughness, so that this is the dotted red is the original vibration without the roughness, and then this is with the roughness. Again, estimates are quite good. However, in order to overcome those problems with the velocity and the surface roughness, we developed a damage index calculation, which is the sum of the difference between the undamaged and damaged breeze in terms of the mode shape square. And that actually eliminates much of the problem. To give an example, so the step we follow, you get the frequency of the breeze and the damping ratio from the vibration test or smartphone, as I showed you before. Then you calculate the amplitude respective of this frequency. Then you reformulate the amplitude, including the damping and other features, and then you calculate damage index. So let me give an example. So this is simulation examples, the same vehicle and the breeze property. Then what we did at the distance 6 meters, we damaged the breeze 10%, 30%, and 50% of the cross sections. We take it away. So if you see on the mode shape, you don't see much of a difference between the healthy one and the damaged one. But using our damage index calculations, you see right at the location of the 6 meter where the damage is, you can see clear peak, and the straight line is a healthy one. So meaning that if you can collect this information from the drive-by vehicle, by seeing a peak in certain location, would tell you something went wrong at that particular location. And also the peak is a directly function of the damage index. So the higher the damage, higher gonna be the peak. It works. So, and so we in real life, you're gonna have a lot of noise. So we also insert some noise into the signal in our simulations, but it's still, again, you see the peak still remains to be seen, and we can clearly see this peak and directing us that something went wrong to that distance. So how about the real experiment then? So in order to test this algorithm, we went to some test. So this is the test setup in the Japan we use. So this is the breeze, scale breeze, and then the vehicle moving. And we have the sensor system in place. And this is the accelerating span. And then this is the span that we are testing the system. And this is the decelerating span. So we have this segment number 2, we're gonna impose some damage there. And we're gonna also run different velocity in a different level. So Here, this is the element we're gonna damage. So we damaged by here, we remove 5 meter of the flange from the millimeter flange. And the second damage, we take 10 millimeter flange of the beam. And third one, we took 50 millimeter flange out of the beam. So we have this damage now on the sections. Then again, as we see, the level of accuracy of the mode shape drops with the high level of damage. But if you compare the mode shape now in a different level of damage, the D1 is the smaller damage, the high level, medium damage, and high level damage. And damage is between the 2 to 2.5 segment. And you can see some anomaly in the mode shape. But if you look at the damage index, it clearly tells you in that location that the peaks are different. So this is really the intact one. That's the damage in the high in the 15 meter damage. This is 20 millimeter damage. So therefore, it's possible to really locate if anything went wrong in the breeze by identifying where are those peaks located along the beam. So it simply works, right? So this is kind of, if you have a damage, local damage is really located in certain location of the breeze. However, the global damage, meaning sometimes, you have like this breeze, right? It's sitting on 4 pier. So sometimes due to the score, your stiffness of the pier get reduced. And can you pick it up? Can you up the change of mode shape from the reduction of the stiffness of the pier from the drive-by? So that was our main goal, which you can call global damage. So in order to do that, so this is the vehicle, again, equipped with the accelerometer that we're going to be collecting. And these are the breeze pier here. You can see there's the first pier, second pier, third pier, and those are the spring. So what we did, we reduced the stiffness of the pier 2 and pier 3 by 25% and the 50%. So we take the spring, we reduce the stiffness 25%, and then next 50%. Same thing we did for the pier 3. We reduced the stiffness by 25% and the 50%. Now we like to see if this vehicle can pick it up, those changes resulting from stiffness changes, and that can happen due to scoring. And we tried it for very different speed. What we noticed that we could produce the mode shape repeatedly, when we run 5, 10 times, especially for the higher mode. And for the lower mode, it was automatic. However, it did not impact our damage index calculation. For pier 3, where your damage actually located at the around 4 meter, that's the breeze pier 3. Remember, we have a stiffness change of 25% and 50%. It's clearly showed up here. And we can see that for 25%, we have this blue graph, and 50% we can see the red one. So imagine you have a vehicle drive through the breeze, and you see those peaks in certain location, you immediately know that your breeze pier has some compromised stiffness. And we see the similar situation in the breeze pier 2, which is located around 2.75, and you can see the jump of the peak showing you, giving you some indication that something went wrong. So this can be applied if you have a problem with the settlement or the cracking on the column, or you have some exposed reinforcements, or something went wrong in the breeze pier or breeze padding. So, and then or elastomeric breeze problem, any global change, it should be able to pick it up. And all of those work that I presented actually published in journals, and I just listed 26 of them. And these are all journals. We have similar number in the conference. So in summary, what I mentioned in this presentation is this, that we know we have the problem that we have today with the breeze inspections, and complement the inspector with health monitoring is a great idea. But as we say, we suffer from the power supply problem, that large volume data problem, and understanding the load and performance issues. And I think we came a long way in this couple of projects by establishing that flyby monitoring with the drone has a significant potential, as you saw. And we also developed drone charging pad and flyby drone sensor both of them would be a major step forward, no doubt. And we also noticed that quality and efficiency can be much improved by having high quality camera and processors speeding. And we also demonstrate how we develop algorithm for breezeway in motion system, where you can get acceleration data from the breeze to give you real time the weight of the truck. And we show you how we can get the damage detection on the fly, and also vibration sensing by hovering drone. And last but not least, we demonstrate drive-by monitoring system, how it would be able to give you the information about the local damage along with the global damage. However, all of those are demonstrated in a very limited way. So I think we need to do more field testing to demonstrate their success. And we really need very high-speed processors that we're currently looking at. With that, I'd like to again thank you, Professor Musharraf Jaman, to give me the opportunity, and my founder, National Science Foundations, and thank you all for listening to me. Thank you so much.
Thank you. Thank you very much, Dr. Uddin. That was very enlightening. We have several good questions too as well we'd like to get through in the chat. Dr. Zaman asks, has any investigations been done on highway bridges, including concrete bridges, steel bridges, and composite bridges? We know that the mode shapes would be different for each bridge type, as well as other factors such as span.
Exactly. That's a fantastic question. So, because this is an NSF project, and NSF looked for scientific breakthrough, and that was our goal. So all of this publication, we have like around 50 publication and 26 in journal. We had to validate everything I say by laboratory experiment. And some of them actually in the actual breeze. Like for breezeway in motion systems, we use a Georgia DOT pre-stressed concrete breeze to show, as you see in the video, that we were able to get the weight of the truck. However, for the flyby drone, and like the drone flying to the breeze and collecting the data, and but we could do it for a railway bridge I showed you. That was a concrete railway bridge, and we could demonstrate the change in mode shape before the rehabilitation and after the rehabilitation of the bearing. But much test needs to be done for sure. And I hope some duty will be interested to give us the opportunity through pool funding or something to show them how this system, as Dr. Jaman said, affected by the type of the problem. Maybe concrete bridge, steel bridge, composite bridge. We should try all of them to identify other limitations might have that we still don't see.
Great. Larry Haberock, I hope I got that last name right, asks, early in your talk, you used the term padding. Is this the same as filtering?
Actually, no. The padding, filtering is like you filter out the noise, or you look for certain signal through filtering. But the padding is like you have like 6-second data, then you add, of course, it's a very sophisticated algorithm. So you extend that 6-second signal to 12-second signal artificially, and still serving and preserving the essence of the vibration. So that's the idea. So we artificially increase the duration of the signal and still maintaining the features. And that duration actually doesn't impact destructively the information from the vibration.
And we have one more from Dr. Zaman. These are actually several questions. What level of training would be needed to get good data? Could DOT personnel and industry be trained to achieve adequate training? How long and extensive would these trainings be?
Again, I think excellent question. So I think that before you get to, I think as Dr. Jaman said in the beginning of the questions, is that we really need to see how it performs in a routinely practical level. So I think to answer that questions, what kind of training we need, I think we really need to work with, for example, Oklahoma DOT say they're interested, right? So if we do 2 or 3 demonstration projects, like one on the steel, one on the concrete, one on some other types, right? And I think by working with them, we'll see and we'll know the gap of technology between us and them, and then we'll be able to see the types of training they need. I really don't have any experience. I know DUTs are very smart. I happen to work with some Georgia DUT personnel and Alabama DUT. They seem in a very, very sophistication level. I think their level was very good. So it depends on really how comfortable they are with the machine learning and algorithm. Of course, I don't think they need to know about algorithm. It's going to be really kind of black box. But I think identifying the challenges and collecting the data in a right way and analyzing the data, I think it will require some training, but I cannot say off the head how much training it is and how long it's going to be due. But they're all definitely practicable, because all of this work done by master's student, PhD student, and I saw them getting up to this speed within a matter of just 1 or few weeks, and I could not see any problem.
We have a couple questions on damage as well. What type of damages have you detected in roadway and highway bridges? Could this technology detect corrosion? And also, damage detection technology seems to depend on comparison of mode shapes of an undamaged bridge and a damaged bridge. How would one have mode shape of an undamaged bridge?
So let me start with the last one. So for the, as I showed you on this railway bridge, and so the bridge was, the support was damaged. So we calculate the mode shape. And then once they fixed it, we calculate the mode shape and we could see the difference. So the idea was then, once you have a bridge, right now, all those bridges that is operational, that we're going to collect the mode shape of, we're going to get the data from that bridge that is operational, and we're going to have information about the mode shape. Then imagine something happened, wildfire came, or some earthquake happened, or hurricane came, or some accident happened. Then you get the signal from the drone. Now, by comparing the mode shape from the drone with the previous mode shape, you know exactly where is happen, if it happened, and the extent of the damage. So to answer your question then, we'll expect to have, like for example, Oklahoma DOT, if we want to implement the system, our first step would be to go all of the bridges, fly the drone, and get that mode shape as it is today. And then if something happened or went wrong, we suspect something, then we go again and compare it. And I forgot the other 2 questions.
Let me see. Scroll back here. Getting quite a lot of questions, a lot of interest generated. This is great. One of the questions, what type of damage have you detected on roadway, highway bridges? Could this technology detect corrosion? And you answered pretty well the other question, I think.
Right. So let's go one by one. So no, we did not focus particularly on the corrosion, but I think it's possible. And what we really focus on, as you said, like the bearing, as I showed you in my demonstration, when the support was really damaged, we figured that out. And then also like the crack on the steel bridge. So we could locate a crack on the steel bridge by image and also by vibration data.
Several more questions to go. Do you know if flyby monitoring and damage detection could be used, or if any kind of testing is done in other industries, steel, telecom, towers?
That's a very good question. I think that's the interesting part. I think I don't see if it can handle the damage location or extent of the bridge to do it in a tower or the column or it should not be a problem, because these are classic cantilever and this should be much easier problem to solve. But we never tested it. But you're right. I think that's very doable, and it's a very interesting twist actually of this idea, that I think it would be much simpler problem to solve.
And what do you foresee the data collection vehicle to be? Semi, large weighted? What minimum load would be required to gather appropriate data?
So is it about the drive-by vehicle, the vehicle that's gonna drive through and then give us the information about the damage of the bridge?
Yes.
So actually we have an extensive paper on that. So we figure out, that's a very good question. So we figure out what kind of range of the weight of the vehicle we need to be and what speed it should be driving. So we kind of optimize that. So we have some publication on that one. You're right. I think it's not all kind of vehicle, but on the average, a typical, truck that LDOT drives across for their maintenance, it should do it. It's not very sophisticated, vehicle, but a typical truck, mid-size
Right. And could this technology be used for load rating?
Yes, yes, that is something. Yeah, I think has a tremendous potential. I think that's the whole
Okay.
idea. That, yeah.
I
Michael, perhaps some of the participants may want to ask questions in person instead of the chat box. So perhaps you might want to give them opportunity to do so.
Sure, yeah. If anyone has any questions as well that they'd rather ask in person, feel free to unmute your microphone and ask Dr. Uddin.
So I have one question that if, for example, ODOT or another DOT were to try this in one of our bridges, whatever it, whatever the type, maybe concrete bridge or steel bridge or composite, how difficult or expensive would it be, for your team to do that and give us some tangible results or outcome?
It would be depend on the types of breeze actually, the span and and the extent of the investigations. So so I really hate to say something off the head. But as I said, I think this technology that I proposed is in a state of really it's dying to be proof tested in the real field. And I think that's the right step. I think to really, for example, Oklahoma DOT look at some of their bridges and and investigate those technology that I just proposed and see it works. But in terms of the budget, in terms of the time, it really depends on the types of bridge and its locations and its age. So it's really not one simple answer.
So if we were to give you some specifics regarding the bridge type and or whatever would be helpful to get an estimate, that might be one way to sort of see
Yeah,
whether Oklahoma DOT or another DOT would be interested. So I think you are right that the NSF looks at developing new ideas. I think that so you covered that pretty well. But I think the next phase, what would that idea do relative to the bridge engineering or bridge inspection practice today? So I think the taking it to that application level would be really very, very helpful and exciting, I think.
exactly. I think one listener actually mentioned that the rating. I'm sure the rating is a big deal for any DOT, and that's what they do. They send the inspector, and he does the quality assessment, and based on the quality assessment, they figure out a rating system, and that rating tells them how healthy and how safe the breeze is. And it's so subjective, and it's such a so limitation. I think this scheme that I propose can really quantify that rating system and take it in a level would be more quantitative and more you can something you can touch, you can feel, and make it more reasonable actually, rather than guesstimate that we do nowadays.
Michael,
All
there are a
right,
couple of other
sounds
questions
good.
in the chat box.
Yes, we have a couple more
Uh-huh.
questions.
Oh,
Let's see. Are there plans for LADOTD or other DOT, as this is NSF research, to test either system in an actual field setting?
So I think that's what right now my team is looking for. So because I think our NSF project going to be concluded this year. So that's what our next step is. Of course, NSF is a government agency. They want us to implement in the real field. And NSF doesn't fund the practical implementation because it really on the DOT side. So this is what we are looking for right now. If DOTs like Oklahoma DOT, Alabama DOT, or Georgia, any DOT, if they by themselves or by some pool funding would allow us to demonstrate this technology in real life and go from there. I think we are in a stage of, as I said, we did some couple of demonstration, as you saw in the Georgia DOT bridge and then one in the Alabama bridge. But I think, but that was a different goal. It was more of a proof of concept. But as Dr. Zaman said, to make it to a practically application level, we need to do some extensive field testing to look into all kind of scenario and proof test that the system can be useful in a routine basis.
All right, and we have one last question in the chat box. For crack detection, can this approach see cracks less than 1 mm in width?
Yes, it can. As long as the drone can come that close. Yeah. It's just depend on the camera, precision camera, and then there's no obstruction between the drone and the location of the bridge, then it can do that. Yes.
So could you also talk a little bit about how you detach the drone? So you are saying that it will attach and then it also has to detach.
Yeah. So it just rotate the rotor in the opposite direction.
So very straightforward, right?
Yeah.
So attaching and detaching, and how expensive is this the system? That you, of course, it depends on the location of the bridge, as you mentioned. But is this fairly inexpensive, or is it
No, these
pretty
are
expensive?
inexpensive. Those drones are very cheap. It's like those drones that we use, it's like a $50-$60 drone max. And those sensors we put using like an iPhone, smartphone sensor. I just took my smartphone apart and get the sensor out of it and use it.
So Oklahoma DOT has several drones of their own. So could those drones be modified, for example, to have that type of feature, attaching and detaching?
Yeah. As long as sometimes it depends on the manufacturer. I think the drone that we bought, the manufacturer allowed us to open it up and insert the accelerator. I think it's doable for most of the drone, but I don't know, Oklahoma DOT might have something that we need manufacturer to do. But we have our own drone these are very cheap, and I don't think we need to fool around with their drone. Yeah, $40-$60 drone is very cheap.
We have
Yes.
one more question in the chat. One's a follow-up to the other industry usage or testing. What would be a practical cost for this system and the drone algorithm testing process to be implemented in other industries?
Yeah, the second, again, I think the first one is about the cost, right? So as I said, the cost actually is not an issue. Drones are cheap and sensors are very cheap. In the matter of couple of $100, I think we can have the system in place. I think the challenge is, that algorithm that we developed and we proof tested them in a lab scale and also just very limited field test. So in order to get it rolling across the board, all kind of breezes, we need to do a lot of testing. And that's what needed right now. And I think that question come again. So this system actually, it can detect damage, not just for the breeze. I think you're right. It can do it for the tower. It can do it for wind turbine. It can do many other stuff because it kind of run with the same algorithm, similar algorithm. But we never did anything on that yet. But it's doable.
Any other questions? Well, if not, then I want to actually again take a minute to thank our speaker for the wonderful presentation. We are sorry that we had little technical difficulties in the beginning, but we did were able to work it out. So give a round of applause, virtual applause for Dr. Uddin.
Thank you.
So thank you again, for taking your time, and please make a note that we are going to have our another seminar in a week. If you are not registered, please do so. And Dr. Uddin's slides, of course, you could take out whatever slides that are sensitive that you do not want to post, will be posted on the SPTC website. And also the video, I think that's something that we are considering, because those who could not attend, will be able to watch the video. Those of you who indicated your PDH, I think we'll look into the attendance, and I think the PDH, Susan will follow up on the PDH, and you will receive your PDH accordingly. So on, we look forward to seeing you in a week, and just stay safe, and thank you all again.
Thank you.